Today we are moving to kind of a new topic, I guess. Previously we've been talking about flow in external situations, and we have like flow over a plate, and the boundary layer can continue to grow. So here we have our boundary layer that we've been dealing with. You have this flow that's coming in at the leading edge of the plate. The boundary layer starts to form. In this case, the momentum boundary layer starts to form immediately, and it increases by the square root of x. If the flow remains laminar, that boundary layer continues to grow according to the laminar representation of that. It will grow indefinitely. Today, we're going to start talking about internal flow. And there's a few things that we have to think about for internal flow that are a little bit different. Fundamentally, it's really the same ideas as external flow, but we run into one complication, and that is, as you, in an internal flow situation, as you're going through, let's say this is a duct, right? So as you're forming the boundary layer in the duct, you're eventually going to get to the point where the boundary layer is going to intersect with the boundary layer growing from the other side. So here we have our boundary layer growing, and then from the top, you're going to also have a boundary layer growing, and eventually they're going to intersect. And at that point, the flow characteristics change a little bit. The boundary layers can't continue to grow. They are constrained in that way, and so we have to come up with different relationships that specifically deal with this region. So we just, for vocabulary, we're going to talk about over here, this is the hydrodynamically, let me get this started again. Hydrodynamically. Okay, so hydrodynamically developing region. Right, that's this portion over here where the boundary layers haven't yet met. And then to the right, we have the fully developed, or hydrodynamically fully developed region. All right, we're going to refer to this position. So if this is our coordinate system, this is x, and x is 0 at the leading edge of the plate. We're going to refer to this position here as xfd. Okay, so x fully developed, that's the position along this tube or duct where the boundary layers actually meet and the flow changes. And let's see, if it's the momentum layer that's growing, so we have like two things going on. We have a thermal layer, and we have our momentum or velocity boundary layer growing. If it's the momentum or velocity layer, we denote this with an H, right? So xfdh refers to the point at which the momentum boundary layers meet in the middle of this duct. Okay, and when that happens, it's fully developed. So what makes this different flow once it's fully developed? Let's sketch out for the hydrodynamic considerations. Let's sketch out shear stress tau. So this would be local shear stress as a function of position x here. And let's say this becomes fully developed at this position here. So this is x fdh. If we're in external flow, what is the shear stress going to do as you increase the position? You're going to start off right at the leading edge. It's essentially infinite. And you quickly decrease, so it looks something like this. Right, so you're continuing to decrease your shear stress because the boundary layer is growing, right? Your shear stress is going to be proportional to the thickness of the boundary layer, inversely proportional to the thickness of the boundary layer. So as that continues to grow, we get a continuing drop in our shear stress. So this would be the situation for external flow. Let's say then we look at internal flow. What's going to happen for internal flow? Well, we have the same in the developing region. We have this overlaying line that's doing exactly the same thing. But then once you get to the fully developed point, we no longer have any change in our boundary layer thickness. Right? The boundary layer thickness becomes constant. And so you get this, sorry, draw this a little bit better. You get a constant shear stress in the fully developed region, because you physically can't, expand the boundary layer anymore. All right, so this is internal flow here. And this was external flow up here. Right, and when this happens, now you have to think about different relationships for internal flow for that region. So we're often going to talk about this developing region, the fully developed region. Just keep in mind, in the fully developed region, that is where you can basically solve for a local value, and that local value is not going to change as a function of position, right? It's fully developed. Okay. Let's. Quite ready for it. All right. So, what does the velocity profile look like in the in internal flow? Let's sketch out a duct again here. There's a duct here. And let's draw the velocity profile as, let's see, we have flow coming in here on the left-hand side. So this is going to be flow coming in at, let's call this U infinity. All right, this is our free stream velocity. It's uniform coming in. Let's introduce a coordinate system. So this is going to be Y and this is going to be X. And then we have at the leading edge, we have a boundary layer growing. So let me just draw that like this and like this. And then let's sketch out the velocity profile at maybe 3 different locations. So first, let's pick a velocity profile in the developing region. Let's pick a velocity profile right. Let's try this again, right when it becomes fully developed. And then maybe one that's a little bit further downstream. Okay. So we start off with our U infinity as constant. As you're coming in, we have this boundary layer growing. Right, the boundary layer is growing. That means that there's going to be a velocity gradient in the boundary layer as it grows. So this is going to look something like near the wall, the velocity is going to go to 0. Right, so it's going to go to 0 like this. In this region now where the velocity hasn't yet been affected, it's going to be the same. It's going to be a constant velocity. And then over here, we again have this. So if you draw the velocity profile in this developing region, it's going to look something like this, right? And as you go further in the developing region, you go further along the development of the boundary layer. Obviously, that's going to collapse down to the point where we get to this fully developed region here. So this is going to look like what? So these are going to fully meet. So like this. So this is your velocity profile when it's fully developed. All right. And one thing I want to be a little bit careful about here. So our U infinity, we drew, it's maybe a bit exaggerated, but it's uniform. It's a uniform velocity coming in. But as we go along here, and especially this region, let's say this region here, I'm losing velocity right near the wall. I'm losing velocity. So in order for mass flow to be conserved, for mass to be conserved, I actually have to increase velocity here. So this region, although it's uniform, is actually getting accelerated a little bit as you start going into this duct. By the time we're out here, this velocity is actually somewhat bigger, right? It's a bigger velocity, as I've exaggerated in the drawing here, than what we had in U infinity. So you could at any point in time take the integral of the velocity profile, the area integral of the velocity profile, and get back the same average velocity. But what you're not preserving is the maximum velocity at any position. Okay, so last thing is we're fully developed here in this third profile. What happens when we move down the pipe further, the duct further? Do we continue to see a change in the velocity profile? No, I see. So it's going to look exactly the same out here. Just believe me that is exactly the same. It's exactly the same as it was when it's fully developed. There's nothing changing about the shear stress. There's nothing changing about the velocity gradient. It remains constant. Okay. So we can, again, write out some maybe notes about what these things are. So we have, here's our delta M. This is a momentum boundary layer. Same thing here. We are plotting velocity. Let's see. So this is going to be maybe at this location here. This is our delta M at x is less than x FDH. This here is going to be this length here is delta M at x FDH. And same thing there. Let's see anything else here. Yeah, again, this is x FDH in that position. All right, so the main things to realize are overall mass flow is conserved. You're not losing mass anywhere from the pipe or anything like that, but you get a change in the velocity profile as you go. It's pretty straightforward. But any questions on this or? Oh, okay. So I mentioned you can you conserve, let's say, the average velocity. So we can write out what that average velocity is. It's called the bulk velocity or the mean velocity. So I've done that already for you. This is going to be U sub m. The mean velocity is going to be the mass flow rate divided by density times the cross-sectional area. Cross-sectional area being, if you were to look down the duct, looking sort of along the axis, the area that you're seeing in that profile. So you have that relationship. You can also express it in terms of volumetric flow rate, V dot. So V dot would be meters cubed per second, where M dot is going to be kilograms per second. Okay, so that's the bulk velocity. One thing that we care about, though, is maybe how much of this flow, or how much does the flow profile affect, say, pressure drop or shear stress in our duct or whatever it is that we're looking at. In order to express correlations for these geometries, we introduce something called the hydraulic diameter. Okay, so the hydraulic diameter is defined as hydraulic. Just note that that's not hydrodynamic diameter. I hear that a lot. It's hydraulic diameter. So hydraulic diameter is, we call that D sub H. So D sub H is just defined as 4 times the cross-sectional area divided by what's called the wetted perimeter. Right, the wetted perimeter is, if you just look at the perimeter of whatever the shape is that describes the duct, how much of that is wet, like what is being exposed to the fluid. So in a circular duct like that, it's just the perimeter of that circle. If it's a rectangle, it's the perimeter of the rectangle. You can get more complicated shapes where maybe it's, those things aren't super obvious, but for these examples, it's pretty straightforward. So for this circle, let's actually just take an example. So DH, this is going to be 4AC over perimeter. So let's do this is 4 times pi d squared. That's our cross-sectional area. 4 pi d squared. Let's see, that's going to be over 4, right? Times the perimeter, which is pi times d. Okay, so no surprise if I go through and cancel this out for pi d squared and d. This just gives us back d. Right, so the hydraulic diameter of a circular duct is in fact the diameter. Right, that kind of makes sense. You'd be a little surprised if that wasn't the case. For a rectangular shape, this is going to be, let's see, dh. This is going to be 4ac over perimeter. So our cross-sectional area here is 4 times a times b, and our perimeter is going to be 2 times a plus b. Okay, so this is actually, I guess, as far as we can go in simplifying it, but that's the hydraulic diameter for a rectangle. So it's going to be something between, the longest leg of the rectangle and the actual, say, radius at any point. It's kind of this effective diameter that we use to characterize the flow. All right. So one question we can ask is, these are just definitions, but we often want to know how long is this hydrodynamic entry length? How long is this x distance that fully develops the flow. So we can go through and solve this in terms of our laminar boundary layer. If we do that, we have delta M laminar. So if you remember, delta M laminar is going to be approximately equal to, say, 2 times the square root of nu times time, right? This is from our 1D conduction model. We can write that in terms of the flow velocity, so that becomes 2 times the square root of nu times x over the mean velocity. So that gives us the growth of the boundary layer. The thickness of the laminar boundary layer at any position x. So all we have to do is rearrange this, where we say, all right, we know that these things are going to meet in the middle. They're going to meet at where delta M laminar is dh over 2. That's the thickness of the boundary layer. So that's going to then approximately equal 2 times the square root of nu times x. So now this x is actually x fdh divided by um. So, right, so square root of all that. It's a bad square root. Let's try that again. So it's the square root of all this stuff. Okay, we can just solve this now for xfd, and we end up with, let's see, we end up with x fd h divided by dh is equal to 1/16 rho times times dh divided by mu. We brought in our definition of nu being mu over rho. And then that actually gives us what? That gives us x fd h over the hydraulic diameter. Dh is approximately equal to 0.063 times the Reynolds in terms of our hydraulic diameter. So if I want to know what is my position at which it becomes fully developed, this equation will approximately tell me that. Where that 0.063 is just 1/16, right? 1/16. So you could keep it exact. I don't know. The book does it with the 0.063, but I guess it doesn't. It's such an approximate calculation, it doesn't really matter that much. But this will give you the length where it becomes fully developed. Okay, so this all assumes that we're remaining laminar. So this is a position at which the laminar boundary layers become fully developed. What naturally you might want to know is what happens if we become turbulent. So how does that change, or when will the flow become turbulent?